So I hope all of you got different numbers than I did, because I lied a little bit. And now I'll tell what the lie is. So in the slide, I had a perfect code with times set to 10, 15, 20, 25, 30, 35, and 5 cycles. But that's only on the slide. In the code that I gave you, it was different numbers. And I beautified these numbers later on. And I forgot to tell you. So you all have different numbers. And the numbers you got are correct for your code. So I'm opening the source, and you see, in my source it's fixed. But in your source there will be different numbers here. 10, 15, 20, 25, so on. You have 23, 27, strange numbers. So let's not spend time on that now. Please try it out later on by copying the right numbers from the slides. Not right, but the version I used here in class. There is no right and wrong here. And you can see that, at least it responds correctly to this times, because it gave you different times when the numbers you used were different. So I'm skipping this. And I think we should be done with sample 1. And the last slide on this sample was suggesting that we go through this work. However, we don't have an automatic way of generating these, so it's only the manual thing. What I do is I change the number of cores on this argument tab. I run it. I just look at the total runtime, and I insert it into a Excel table on the side under the TP column. That's it. And then in a speed up and efficiency, I just have the numbers computed. Let me find out this original Excel, not in a slide. Original Excel. Let me see what it is. In my shared disk, just a second. Speed up. This is my Excel where I generated this. So I only entered these numbers. You see, this is the number I got for the whole thing and so on. And I went all the way through to 1024. Then in speed up, the first one, what I did is actually, I don't know how to increase that much longer, especially I don't know how to include the formula, but you see the formula. So speed up is this number divided by itself. But for number 2, it's this number, T2, divided by T1. So, T1 divided by T2. So $2 means always look at this constant cell and divide it by this variable. So in this case, B3. And then on and on and on. So all of these divide this TP by T of 1. And this is how you get these speed up numbers. The efficiency is the same as a speed up number divided again by the number of cores, and this is what we get. So 838 divided by 1024 is only 0.82. Going back to my slides, to the previous one, Speed up is T1 divided by, let me just increase that and get my pointer back. Speed up is T1 divided by Tp. Speed up of P. Usually speed up of P is less than P. I cannot run on 64 cores and run any faster than 64 times faster than on a single core. If I get a speed up that's faster than the number of cores, there must be a bug somewhere. So this is a good reason to start looking for bugs or for incorrect ideas of what the numbers are. Efficiency is a total work divided by possible work. Possible work was the length of the runtime on P processors times the number of processors. Now, usually work is the same as T1. In a minute, I'll tell you when it's not the same. But usually, the total work is the same as the T1. So, efficiency is speed up divided by P, because if I do work, replace work by T1. So I have T1 divided by Tp, P. But T1 divided by Tp is always speed up, so I only have to add P in the denominator, speed up divided by P. And the efficiency is less than 1. If I get efficiency bigger than 1, look for the bug. So that's very simple. So here is what I got.
Can I make a comment?
These are the, yeah, please comment.
You're comparing the speed up against the single thread version, right? Or single task version.
As opposed to?
That's okay, so you don't change anything about any compiling options and so on, because that's actually indicators.
Okay, so here's an important comment, but before your comment, I'll make another comment. This is a very simple program. It does what it does, regardless of how we organize how many cores. We don't change the code at all. The code stays the same. Sometimes, when we write a parallel program, we say, you know, we can do a little bit more work than needed, but speed things up. For example, if I need to compute a number, and then everybody needs the same number. I need to compute the number once, and then everybody uses the same number. So, one task, compute the number, puts it in shared memory, and then everybody else reads it. But I can save the time to read from shared memory. Because in some machines, it takes, let's say, 2 cycles to compute the number, but 100 cycles to read it from shared memory. So I'd say, why? Why do I care? Let's say I have 100 processors. Let each processor compute the same number. 99 redundant computations, only one is needed, but I'm doing 100. But it's much faster because everybody takes 2 cycles to compute the number instead of trying to save, compute it only once and write it in shared memory and then everybody reads it from shared memory. But reading takes very long time, 100 cycles. Or let's say, not in this machine, but let's say general. And even worse, let's say there are many conflicts because everybody now wants to reach the same place. So they are serialized. So 100 processors, each of them spending 100 units of time just reading from shared memory, and they are serialized because they keep conflicting. So I'll spend maybe 10,000 times for everybody to read a shared number, instead of just having everybody do some redundant work and recompute the shared number. So the total number of work will be not very schematic as here. Total number of work, I'll do extra work in order to speed things up. In that case, I get different numbers, and in a formula, I cannot use the claim work equals T1. So I have to do real work, and real work may be bigger than T1 because if I ran everything on one processor, but my code says, compute these number 100 times, because I thought I was running on 100 processor, it would be stupid. So there are many ways to play with this, and this is very schematic, but we'll go to more interesting examples later on where we bypass all this. Now, what Jamin, so talking about our example, Jamin comes in and says, look, this is stupid.
No, I didn't say.
No, I'm saying you say.
That's okay.
So I'm saying, Jamin saying it's stupid. In this, if you run it on a single core, why compute 100 times the same number? You know you're in single core, write a special code for a single core. Compute it only once. And do other things. Tell the compiler to optimize, because it's all running on the same core. You don't have to go in and out and share memory, just keep things in temporary memory and so on. Local memory. So you do a lot of optimization, and suddenly T1 is not, it's completely different. If you open a textbook about parallel processing, the textbook will say that we have to follow Jamin's guidance. When we really do comparison, we should do a fair comparison to the best possible program on a uniprocessor. But we are not playing this game here, because we don't really care what it is on a single processor. We just use it in order to identify problems in parallelization, which we'll show later. So we ignore the good advice from Jamin and continue with this naive way, because this is much easier on day one of learning how to do parallel processing. Second sample is matrix multiplication. We're already ready to go the next step. Usually matrix multiplication, these are two matrices multiplied, and each element of the elements I in row I and column J of matrix C is the sum of A, I, N, B, and J. So this is a dot product, scalar product of two vectors that a guy was showing earlier with a nice program inside the DSP. Of course, we now do a much simpler, more naive approach. Each result is computed by one task. In our parallelization, we have one task to do one. Cij is one task. So if we have matrices that are n by n, we have n by n tasks. Each task computes a single result in the result matrix. Later in the next sample, each task will do something else, will compute an entire row. And I separated the two examples because the results are completely different, and they are designed to show us how to do right parallelism or wrong parallelism, or play the game in what you expect. So the code is simple. Let's go over the code before we open the code itself. So we have now include a standard lib just because I want to have a printf. And we have a define statement. Matrix size is 100, so the matrix will be 100 by 100, a total of 10,000 elements. I usually, on my machine, it runs extremely fast, and on every machine here, I'm sure it will run fast. There's small matrix for us, just 10,000 elements. We go to floating point. So we use C language floating point, easy. A is n by m, m size by m size, B and C, three matrices, very simple. And here is the first task, the program start. Obviously, it runs once in the beginning. By the way, the next task will be called NM for matrix multiply, and will be executed n by n times, 10,000. And the last task will be program end. So the task graph is so simple, I don't even have to draw a picture. look at the task graph text on the right, regular, duplicate, regular. That's it. So you do the program start once, run these 10,000 times. It says nm size, and nm size is defined as this. By the way, we run the task graph through the C preprocessor in order to execute these macros, define, and we can have other macros. Not everything works, but these are simple. We can have if-def, if-ndef, and so on, other macros that are typically used in C. So this is extremely simple task graph. I don't have to draw the picture. Program start actually puts values into A and into B. For all values of I and J, A gets the number 13 for good luck, and B gets 9. And then we multiply them. Of course, in the code that you will find in a virtual machine, we also have commented out another possibility to just use random numbers, but it's much simpler on the slide for PowerPoint engineering to just use very simple code. And then the matrix multiplication, that's very interesting. We get an ID number, and then we decide what the I and J are out of the ID number. ID will be anywhere from 0 to 9,999. And I is the ID modulo m size. And J is the remainder of, well, ID divided by m size. Oh, sorry, not the remainder, the main number. So the column number is this, and this is the modulo. So I is the remainder, and ID is the integral division. And this will give you, this will generate, very simple way, will generate all values of I and all values of J from 0 to 100. M size is 100. 0 to 99. And then we run the value M on, for the dot product, M from 0 to M size, sum, which sum is initialized as 0, sum is incremented by AIM times BMJ. Just like in the previous page, I had it on the, let's see, on the nice formula right here. Very simple. And at the end, we take the sum and store it in shared memory in CIJ. So everything was done locally in the core, but at the, only at the end I go to the global variable, which is in shared memory. Notice the definition of, or declaration of A, B, and C. It's global, it's outside of the function or the test, so it's global and it's a shared memory. That's how I say this value is in shared memory. But notice inside this function, I and J are declared locally. They are local variables, private variables of each instance. They never get to share memory, and we guarantee that it don't do it by, because they are defined on a stack, and the stack is stored locally in each core. So although many instances use the same name, each one has its own. That is true in C language as well, and in a task model as well. In the end, we just print finished, but of course we can also print the values of the matrix if you want. So very simple. Two constant matrices are generated, and the actual code includes optional random number generation and optional printout of the outputs, and that's it. So I'm looking up into my code. Where is the virtual machine? Even right here. I'm closing for cleanliness. I'm closing sample 1 and opening sample 2. It's called matrix multiply with n square tasks. Right click and open project. Click on the pull on the arrow. And there's a lot of things here, but here is a task graph. Again, you see 5 lines, 2 defined and 3 lines in a graph, so there is nothing interesting here. Does it work? No. Okay, so back to this. I was trying the graphics, but the graphic doesn't work here.
Maybe when you're done with your explanation, I can ask a question. Maybe also
show the graphics
for the other participants.
Okay.
There's one thing.
Please go ahead.
So here you set the task instance number statically. Is it defined?
Oh, so it can be done dynamically, but that's another example.
Okay.
I hope I
I think we should tell them how to do this so they
yeah.
play a little more.
We set for
Yeah.
So he's right. So maybe I don't know the numbers in ahead of time, and rather than define, I have code which reads unexpected data and say, this is the size of the matrix. Okay, now I need to dynamically allocate the values. I use malloc, normal malloc. To get dynamic allocation of space for the matrices, and I also have to determine how many times I need to run this task, duplicable task, and I do it also dynamically in the code of the program start. In the code, depending on the size of the matrix that I have read from the input. And so that there is a function called to set the quota of a task. But for simplicity, we skip it here, and let's look at the code, just to make sure that the code is as simple as I was saying. Of course it's not. So I have a few more things defined, but before I go into them, I want to show what happens with the code that I was showing briefly on the slides. So back to the slide, and if I use this, notice that none of these had set task time function code. I didn't set the task time. What I did is I let my Linux virtual machine determine what the task, and the emulator agrees. It asks the machine, it asks the virtual machine, which asks Windows operating system underneath, which asks my processor within the laptop, what's the time now? And again and again and again, and they compute on the difference, and they just report the times automatically, and then I get the nice results, and I draw the graph, and I get something horrible like this. And that's not good, because it doesn't make sense. What we have here is the same graph as we've seen before. This is 64, and then I go to some arbitrary number, and then down,